Hello. Hello. Okay, so we are live and we'll solve graph problems today as well. Okay, so we are live and starting with road reparation. I am skipping some of these planet questions because we will solve them later. First, we'll solve these road reparation problems. Okay. So what the question states is that we have n cities and m roads, and the condition of the roads is so poor it cannot be used. Repairing some of the roads so that there will be a decent road between n cities, and we have to find the minimum cost. We are given the cost for repairing each of the road. Okay. So see, this question is nothing but a roundabout. This question is nothing but a roundabout way of asking the minimum spanning tree of that graph. Okay, so road reparation. So it is asking us the minimum spanning tree only. And how do we solve it? How do we solve MST? So we have two algorithms. Okay, we have two algorithms. One is Prim's and one other is Kruskal's. So Kruskal's uses DSU, I think. Disjoint sets. It uses disjoint set. And other one, Prince uses your normal priority queue. Okay, and the difference between them is that we will start with the arbitrary node, okay, in Prims, and we'll keep adding the minimum weighted edge to it, and we'll keep track of the visited node. Unlike Dijkstra, where you do not have any visited or tracking basically for nodes, here in Prims you will have one, and if it is already encountered you will not add it to the cost and simply skip it. Okay, there is a slight difference, basically a one or two line. It is not that much different from Dijkstra. So we have that, or we can use DSU, but for DSU we need to write a lot of boilerplate code also. So what should we do? Should we go with Prims or Ruscals? I can do both. I can try to do both. Okay, let's try to do both. So okay, so it is basically minimum spanning tree. Okay, and we can use either Prims or Kruskal's algo. How does Prim's algo work? Basically, we will we will start with an arbitrary node. We will have a priority queue, or basically min heap. We will start an arbitrary queue, let's say 1. So 1 will be in the queue, okay, and it will be with the weight also. So we will associate the node with its weight. Or should we? No, we will associate an edge. Okay, an edge will be like how was it this implemented? C++. Okay. Yes, similar, very similar. We'll start with 0 0. Okay, and then we will add, and then we will add the, or we can start with 0 1 if it is a 1 based indexing. So we'll start with 0 1. Right now the MST weight is 0, so 0 1 is here, and we pop this out. We will traverse in the graph looking for its adjacent, so we will have 1 going to 2, and we also have 5. We have 2 going to 3 and 4, and 5 going to 4, 3 going to 4. So we have a graph like this. So we will start with 1, and then we will put its adjacent down in the queue. So we will have basically 3 and 2, and we'll have and we will have this only. So this edge will be included then, and now we have this edge is already done. Okay, then we have these 2 edges, so we have 3 5, or sorry, 5 3 or 2 4. So obviously 2 4 will be chosen. 2 4 is now here. Okay, and now we are done with this. I think I have some of the code for Prim or Pascal. Okay. So the dry is simple. I don't know why I was making it complex. Okay. So we have a queue. First we'll put 0 1 here. We will pull this out. Okay. We'll push these edges with their weights. So we have basically 3 2 this one and 7 5 this one. So the smallest one out of these is 3 2, so we'll include this edge. This edge is included, and then we will add all the adjacent edges to the queue. So 1 2, so these two edges, so basically 5 3 and 2 4. Out of all the edges, the lowest one is 2 4, so we will add this edge in the MST now. Again, 4's adjacent edges will be included, so it will be 5 or 4 5, and then you have 8 3. Okay, I'm pairing them with weight and then where the edge is going to. Okay, so out of these, the smallest one is of course 4 5, so we will include this path, this edge. Okay, after that there is nothing, so we will not add anything, and this edge will be removed. And then we have 5 3, so 5 3 edge will be added also, so this edge. So now we have the minimum MST, so basically 5 4 3 and 2. 5 4 9 3 12 14. This is the answer. Okay, so let's go and implement this. Need int nm. Okay, and then we will need edges. We will need adjacency matrix. So EPII and adjacency matrix of size basically n plus 1, and we'll take input in this a b w. Done. And then a b w done, and then we'll do this. B W A W. Okay, we will keep track of the visited node. So visited nodes. We will have MST. We will have a priority queue. So this will be this should work. I'm not sure. Let's try to see. 0 1 1 2 2 3 4. So it is the shortest min heap. So we have a min heap here, and then we will push this 0 1 in the min heap. We'll start from 1. Okay, and we don't need this, it was just for testing. So okay, now we need this we need to do this, and also we need to do this. Okay, after this okay, so a minimum spanning tree will have n minus 1 edges only, right? So if we try to do processing for all the edges in the queue, then it will not give us a correct answer. I think let's try, let's see. So if it is not visited, then only we will put the edge in the priority queue. So it will be the node weight and node this. Let's see. So n steps is equal to n minus 1, or rather n. Okay. So we don't need to process all the priority queue elements. We need only process n minus 1 edges, because by then we will get the minimum spanning tree. So this will be one of the solutions, I think. Another one is your DSA solution. I hope it works, please. Okay, it doesn't. Why? Okay, I didn't factor in the cases where it will be impossible to reach the. It will be impossible to make such a, it will be impossible to repair the roads. This one. So. When will it be impossible to repair a road? Basically, if we, after even repairing the road, we cannot reach that component or that area, right? So basically, if we have components, okay, that are not connected, so to check that, we can just do a simple BFS, right? We can do a simple BFS and sorry, DFS, and I think I should just do DFS here only. So auto DFS is, and I will have a source here. It will not return anything, so, and here we will do with src s2, and for auto node in that send src, if not with node, then we will do DFS with that node, and this should do. And here we will check if for all the I starting from n to n plus 1, if we have not visited any of the node or even a single one, then in that case we will not be able to okay, so need to run. Okay, Okay, lambda function cannot do this, so I'll have to do it function. What is it called? Inline functions? No. It's not called inline. Okay. This auto ampersand self, and I will do self. Will it work? this thing, this thing. So I will need a function, and there will be a type. So I suppose this is input and this is output and this is input. There is the name. We have this capture and src, and then our usual thing. Okay, so it is compiled. Now here we will do again this dot dot clear. Or we start re assign. Yes, assign. Is dot assign n+1 with false. Okay, now I think it should work. Some of the functions I think I need to revise, like this assign, and you have replace also. Replace, I think. Okay, we need long. Okay, so ll done. So this was Prem's algo. Okay, this was Prem's algo. In Kruskal we will need DSU. Okay, so how the DSU solution works? In DSU, what we will do is we will sort the edges based on weight first. Okay, so after we sort this, so it will look something like this. So 2 4 2 and 1 2 3 5 4 4 and you have 2 3 5, you have 5 1 7 and you have 3 4 8, so 6. So you will start adding them in the disjoint set. Basically 2 and 4 are connected, so 2 and 4, this edge will be added to the MST and 2 is added to the weight. Okay, after that 1 and 2 is also connected, so 1 will also added and the weight is also added. 5 and 4, so 5 is added with weight 4. Okay, and then we have 2 3 2 3, so 2 and 3, so with 5, so this is also added. So we have 2 3 5 4 9 5 14, so 14 we already have. Okay, now 5 1 7, we know that these are in the same component. From DSC we will know, so we will not add this, so we will discard this. 3 4, these also are in the same component, so we will not add this, discard this. So finally we will have the answer as 14, and this is our optimal tree. So DSC also has two types. One where the components are basically joined based on rank, and the other is where they are joined based on size. So I found the size one to be more intuitive, so I will do just that. So we'll have public and we will have a vector of basically size. We'll also have a parent, and by initializing DSU with a number, we are setting the size, we are reserving the size, basically how many elements there could be in the component, maximum. Okay, so we will do this. It will be n plus 1 and the size initially is 0. So for parent also we will do and initially all the elements are having parent as themselves only. Okay, so it will be like this. Okay, so it is done. Now we have two major functions. One is finding parent. Okay, so find parent, we have this. So I'm going to do it like this. We have a source, let's say u. We have this. So u is basically a node of which we have to find the parent. So we have stored the parent information in this parent array. Okay, so the thing is that when the nodes are added in a component, right, the parent will choose only single element to be its parent, because we don't need the connection itself, but the the quality of them being connected in that component. Okay, you if you're able to understand, so basically we don't need the connection itself, we need the fact that it is connected to that in some way, that node in some way, or basically it is in the same component as that, and it is acting as a parent of it. Okay. So thing is, in a component there will be one element for which the parent array's value for it will be itself only, because it will not because it is the like super parent, right? It's parent of all things, but there is no parent for it, and since by default we have set the parent to itself, so that super parent will have the value uh, will have the value set to itself only. So if in any step, at any step we encounter that the parent of u is simply u, then we'll just return this. Okay, otherwise what we can do, we can return the parent of u. Okay. What this does is basically is recursive step for reaching the parent. We are finding the parent of the parent. Okay, and one more thing is that we can try to compress the path. Basically, if we find that this node is parent of something and this node itself has a parent, then instead of going through jumps, instead of going through like this node and this node, let me do it like this. So let's say we have this node right here. Okay, we had one initially, we had all the nodes here, all of them parent. There was 1 2, they were parents of themselves initially. We joined these two. Okay, so I made a decision that 1 will be considered the parent of 2. Okay, I made a decision that 1 will be considered parent of 2, so its parent will be now changed to 1. Okay, now 2 again we have, okay, let me do it like this. We added 2 and 4, right? So we added 2 and 4. So I made a decision that 2 will be parent of 4. Okay, so it will be 2 now. And then 1 2 3, 1 2 3 is so 1 and 2 are connected. So I made a decision that 2 is parent of 1. So it is now changed to 2 also. Then 5 and 4 are connected, so again this. So instead of trying to attach 5 to 4, why not we just attach 5 to 2 itself? Because we don't need these edges to be we don't need to store the edge information, we need to store that they are in the same component only. So for that, parent of 4, it doesn't matter if parent of for that we don't need the 4 and 5 connection. Basically we will just get the parent of 4, which is 2, and then add 5 to it. Okay, thus making the future queries, or basically future future queries simpler or easier to answer. So all of them have all of them now 2 as the parent. Similarly, if we add the last one, which is 3, so 3 will also be added here and its parent will be 2. Now if there is another edge, so what we'll do is we'll just check its parent, whether its parent is 2 or whether their parents are same. If they are same, then that means they're in the same component. If not, then they're in a different component. Okay, so this is the basic logic, and what this is basically, this is path compression. So I will save the parent info here only. Okay, now one more thing, we need to add the edges to or basically we need to add nodes to the component. So how do I do it? First we'll need to find the parent okay. And if the parents are not same, then only we'll proceed further. Otherwise there is no point in it, because why would we need to combine the two nodes which are already combined, right? So we will check one thing. I am adding or combining the nodes based on the size, obviously. So if the size of parent of u is greater than or equal to size of parent of v, so what we will do is we will add, so parent of v is parent of u. The size of parent of u plus equal to size of parent of v. Then we have combined them. Otherwise we'll just do the opposite. So parent of u is equal to parent of v, and size of parent of v plus equal to size of parent of u. Okay, so yeah, we have combined the nodes, we have find the parent, so DSC is complete and input is also complete. So all we need to do is we will sort the edges. Okay, and one thing we can do is we can, instead of instead of having adjacency list, we can have a edge list. So that edge list will have three fields, right? U, V and W. So we will have this. So we will have V, V, L, L, and I'm going to let this edges. Size is n+1, and we have 3 sized. That's okay. So okay, we don't need to do this. Okay, then edges I and 0 is A, edges I1 is B, edges I2 is equal to W. So we have the edge list. Now we will make a DSU of n size. We will sort the edges. We will sort the edges based on the weight. So A2 is less than A B2. I think this should work. I'm not sure if this should be less than, or okay, we'll see. If the answer is wrong, then of course we need to change this. So we have changed it, and now we will just traverse in the edges and check. We'll check what? We'll check two things. If DSU dot find parent of V0 is not equal to DSU dot find parent of V1, then we will unite these two. ST will be added to V2. Okay, otherwise we don't need to do anything. Let's see. The answer is same, so I think this should work. Please work. Runtime error. Okay, why runtime error? Empty. Okay, so impossible output. I have not think turned. Will it be impossible? Again, Okay. So we solved this question again. Number of components and the size of the largest component. It is very similar to that the current question. So should we solve this now? I mean, I can. Let's solve this. Okay. Road construction, road decoration, road construction. So we have road construction problem. So there are no roads initially, so basically we have n different cities, so n different components. Okay, n cities. So we have n cities. So every day we are making new roads. So suppose one day 1 and 3 are connected. Okay, so now we have one less cities. One less city means one less component. So initially whatever we have, let's say n components. So after making a road, the component will be decreased to n minus 1. So we know that every time a road is made, component will be decreased, right? And the maximum size of the component. So if we add a road, what we are doing, basically we are doing a union of two nodes, right? And if its size is initially 1, then after adding 3 to 1 it will be 2, right? So after union we are doing two things. We are doing component minus minus, and also we are doing what is the maximum size, and we are taking the maximum of that size and whatever the combined component will give us. So size of this parent basically. So this 2 will give me the answer. These 2 will give me the answer. Okay. 3 roads and 3 output. So let's remove the edges. Do we need the edges? No, it's a purely DSC problem, so I don't think there's need for any of this. I don't think we need to even this. Okay. This and auto answer is equal to DSU dot unit U and V. There is a new road every day now, so answer dot first, answer dot second, and done. Okay, so with this class we'll have to store two more things. One is the max size, also the other is the number of components. We will initialize it, components to be n and the max size to be 0 initially. We don't need parents. No, we do need parents. Size is also 0. No, size should be 1. Na? Size should be 1. Then everything is okay. This is also okay. And here we will return a pair which will contain the number of components and the max size till now. Anytime we combine this, component size will decrease and the max size is maximum of max size comma size of parent of u or parent of me. This should work. Don't need MST. Let's copy the input. Four, 2, 3, 3, 2, 3. Okay, let's submit it. Done. And cities M-Flight connections using the available flights. One flights. This is also a component question, I think. But for directed graphs, components is a little tricky because there are scenarios where you can reach from A to B but will not be able to reach B to A, and thus will require a different algorithm for finding the strongly connected components. We don't have connected components but rather strongly connected components, and we use an algorithm called Kosa-Raj's algorithm. We will use that and find the answer to this. We'll try to find the answer to this tomorrow. Okay. After that, planet query, cycle, character, pizza, a lot of things. We will do that. Okay. So I guess this is it for today. And yeah, till the next stream,